Today we will share our recent work on the cleanability and the paintability study of cast aluminum in the paint shop. For the background, unit casting is being valued by automotive because it can consolidate parts and simplify the process. For example, here there are 171 pieces of the mixed metal highlighted in the body structure. With unit casting, it can be consolidated into just 2 pieces, the front and the rear. And with this reduced parts, the joining can also be reduced significantly. For example, here there's 1,600 fewer wheels joining. Unit casting can be made by high pressure die casting technology. Normally the molten liquid is injected into the chamber and they can solidify quickly and they take a few seconds to make one casting. The liquid metal has a temperature like 700 degrees C, and it can potentially react with the die surface and cause some diffusion and make it difficult to release from the die. So lubricant normally applied on the die surface, no matter the cover side or the ejector side, so it can form a protective film. But you can imagine with the contact with the liquid metal, the lubricant can be oxidized and leave some residue on the surface. After the casting process, the part may be machined or trimmed, so there you can imagine there can be some coolant or lubricant. So the casting must be cleaned and maybe sometimes require pre-treatment E-coat. So one typical pre-treatment or E-coat process is we send the part to the E-coat company, and they do the cleaning, pre-treatment, and E-coat and cure. Then the E-coat part is send the send the OEM body shop. It can be assembled with other metal substrate, then pass through the paint shop again. So if you look at the process in the E-coat company and also in the OEM paint shop, they are kind of similar. So we are thinking whether we can directly do the pre-treatment E-coat in the body shop because they have the similar process. And with this new approach, they can potentially reduce, simplify the process and also reduce the cost. But the paint shop process has been optimized to get a better performance on the existing mixed metals. If a new material is introduced, we have to study their compatibility with the current process and then see whether any change is required. So to evaluate this compatibility, we look at their cleanability and paintability in the process. So we look at the edge loss in the alkaline cleaning and also the zirconium pre-treatment on the surface. And also more important part is whether the lubricant on the surface or coolant on the surface can be removed during this alkaline cleaning process. Then other pre-treatment also put some E-coat to provide good corrosion protection. Normally we evaluate their wet adhesion, also quite quick performance. In order to evaluate this performance, we needed to have better, look at what's the process in the paint shop and also look at the mouth structure or this new material. Then we can have a better understanding what might happen in the process. So first, the surface treatment process in the paint shop. Here we use an example of the stamped aluminum on the surface. Normally you have a lubricant. You also have dirt. You also have some oxide, maybe from the heat treatment or from the rolling process. First, it will be cleaned in the degreasing solution. Normally have high pH. It can be hydroxide based or can be other chemical based, and also some additive like surfactant to remove the lubricant from the surface. It can be immersion or spray or both. So the purpose of this process is to remove the dirt, debris or stamping lubricant. Also, so you can get a clean surface, especially oil-free surface. Then you're also trying to maybe control the etching, so you can etch the surface for the subsequent pre-treatment. And here we're more focused on the sand film or the zirconium oxide-based pre-treatment. This is a key chemical, and also sometimes you see some additives to either increase the coating formation rate or get a uniform conversion coating deposition. So after this pre-treatment process, you can get a conversion coating on the surface and the key requirement like the coating weight or the uniformity. Then the pre-treated part is sent to the E-coat bus. You can apply your potential and get some polymer deposit on the surface and cured. And you can see here the key process for the new material in the paint shop is the alkaline cleaning and the pre-treatment. Especially the alkaline cleaning is the critical step to clean the surface and get ready for the subsequent pre-treatment. Now we know what's in the paint shop process. Then we also want to know what's the alloy and especially the mouth structure, because this is the we need to talk about both chemical and also the metal alloy to understand their reactivity. And in the cast aluminum normally has a very high amount of silicon. It can be 6 or something can be even higher than 12%, depending on the alloy you use. Because the silicon normally exists in the eutech structure or silicon aluminum phase. Normally it's a layer structure, silicon, aluminum. I want to mention this, so emphasize this phase because we keep talking about this eutech structure. It's a layer structure, aluminum, silicon. The aluminum is still the key element in the alloy, so it mainly exists in the alpha phase. It's like a pure aluminum. There are also some other second phase particles like the mounted iron silicon particles. So this is the 3 key phases in the mouth structure. But I also want to mention there are some difference between the top surface and the center because during the solidification, the cooling rate on the surface is much higher, so you may get a fine mouth structure and smaller grains. Another interesting thing you might see is the darkness. So the top surface is darker than the center. So we care about top surface because really the top surface that react with the surface treatment chemicals then can affect the subsequent coating or performance. So now we know what's happening in the paint shop. We also know the mouth structure and also the chemistry of the alloy. Then what happens if you dip this alloy into the pre-treatment or cleaning solution? And you may look at, when you look at the commercial product, there can be many different compositions. So here we're just trying to use a simplified metal stability at the pH to get an idea what might happen. And this is solely based on the thermodynamic data, but it can be very useful to predict the behavior of new material in a new system when the information is limited. So you can see, in the alkaline cleaning solution, the pH is normally high, so aluminum can corrode and form aluminate. But if you look at the silicon, it can form a passivation layer, silicon oxide, so it can protect the aluminum from dissolution. So now if you imagine you dip the cast aluminum, which has high amount of silicon, and in the high pH alkaline cleaning solution, aluminum will dissolve, but silicon will passivate on the surface. So this is solely based on the thermodynamic data, but what happened if, let's see what happened on the real cast aluminum that dip in the commercial products. And this is the surface morphology with the cast aluminum at different stage at the cast condition, after alkaline cleaning, and after zirconium pretreatment as 2 different magnification, 3,000 and 10,000. You can see at the cast condition, it's pretty smooth. You may see some small particles over here, but after the alkaline cleaning, the surface becomes very rough and actually showing some porous structure. If you look at the magnification, high magnification, you can see it's a layered structure, and it's mainly silicon. If you remember, so this is more like the eutech structure. It seems the aluminum layer dissolved and just leave the silicon on the surface. Also, you can see some enrichment or the mounted silicon iron particles. And after the zirconium pretreatment, you do see something deposited on the surface, especially if you look at the layer, the gap between the silicon layers is getting much smaller. So it seems there's a lot of etching on the surface, and also we put some zirconium on the surface. And we did further understanding to see how thick was this porous layer and how the zirconium form on the surface. And so this is the cross-section was a pre-treated sample. We put a carbon on the surface just to protect, to avoid etching during the annealing process. There, the red line here is the interface between the porous structure and the metals and the metal substrate. There are mainly three interesting things from this cross-section. First, this layer is like around 900 nanometers, and if you convert to the etch loss, it can be very high. The second thing, if you look at the silicon phase, you see this layer structure is continuous from the metal substrate, but the aluminum between this silicon is absent. That meaning there is some selective dissolution of aluminum during the alkaline cleaning process, and they can leave a silicon-rich layer on the surface. The last thing is the zirconium. If you look at this zirconium distribution in the porous layer, it's pretty uniform, but limited by the resolution of the EDS, it's difficult to tell how this zirconium deposit on the surface. If you deposit on the silicon phase or the aluminum phase or both phase. So to have a better understanding about this zirconium formation on this porous structure, we did a TEM analysis. So we take a small sample here, and this is the cross-section. And you do see this porous structure. This is the silicon, and there's some porosity under the silicon. And if you look at the zirconium distribution on the surface, back and forth, you can see it's covered almost all the free surface. You do see here the bright dots is artifact during the EDS analysis, so nothing over there. So it seems that the zirconium covers the whole surface, but this alloy has, the porous structure has very high surface area due to porous structure, so you can imagine the coating rate can be very high. Then now we know what zirconium can form on the surface, but we know in the mass structure there are three phases, so we just take a further look at each phase to see any difference in the zirconium deposition. So first on the aluminum phase, this is aluminum, and this is the zirconium. They're pretty uniform. And this is the silicon phase. This is the manganese iron silicon particle phase. Also, it's pretty uniform. Actually, we measure the zirconium thickness on each phase at different locations. Actually, the layer is similar, around 15 nanometers. So zirconium pretreatment has been well studied on aluminum alloy, like a body sheet or extrusion. So we know what happened on pure aluminum, what happened on the manganese silicon iron particles, but there's very limited information about its formation mechanism on the silicon, because based on the current understanding on the zirconium formation mechanism, seems it shouldn't form very thick or uniform zirconium pretreatment on the surface. So to have a better understanding what happened on the silicon phase, how the zirconium form on the silicon, we did a further analysis on the deposition on silicon. So this is the this is a high magnification or the precipitates on the silicon particle. Here is 100 nanometer. You can see this is kind of a round copper-rich particles. Normally you do see this a lot in the aluminum body sheet or extrusion, but here you see this on the silicon. But how the copper formed on the silicon phase is a chemical reduction, or it's just some hydroxide precipitates. This is something very interesting, and also we get a chance to look at the cross-section of this particle. You see, it's not just on the surface. Actually, it can just directly deposit on the silicon. So this is one thing. The second thing is here in the silicon, there's some area without this copper, and does any copper on the silicon surface, and it can promote this zirconium formation. So we did a line scan from from the silicon phase to across the conversion coating. You can see beginning the silicon is very high, then you see a zirconium peak, and that's the conversion coating. You do see copper peak here, and also another peak outside was the zirconium conversion coating. Then it's really come to an interesting question, why the copper can deposit on the silicon, and what's the driving force for the zirconium formation on the silicon phase. So And because based on the understanding that zirconium conversion coating formation is a pH-driven process, and you need a local pH increase to trigger the zirconium precipitates. So there are many, now there can be two mechanisms. One is a oxygen reduction reaction, so you can oxygen reduce the pH will increase, pH increase will trigger the zirconium formation. Another mechanism is the metal acid reaction. As acid is consumed, the pH will increase, especially this is for the active metal or some coil pretreatment with a strong spray. This metal may probably more dominant, but silicon is not a strong cathode to support oxygen reduction reaction. Also, silicon also very stable in the acid. So how the zirconium form on silicon? So to have this better understanding, we did a simple test. We instead would do the alkaline cleaning pretreatment. We polish the sample so we can review the mouth structure. The eutectic silicon, aluminum, this kind of layered structure, and also review the pure aluminum phase, and then dip this in the pretreatment solution. And if you look at the zirconium, so this white precipitates on the surface, they had high copper and also zirconium, and this deposition pattern match very well with the eutectic mouth structure. And if you zoom in this local area, you do see this precipitate is like a layered structure. This layered structure, it can be silicon, it can be aluminum. In our understanding, copper can be reduced by aluminum, then form a copper layer, then promote the zirconium pretreatment. But in this case, it's probably different because if you look at the EDS mapping with the copper and the silicon, they are pretty similar. If you put these two elements in one map, they overlap very well. This indicated the copper mainly deposit on the silicon face, but not really on the maybe lower deposition on the aluminum face. I don't want to see no copper on the aluminum face. So based on this simple test, we think the potential mechanism for the zirconium formation on the silicon is the galvanic corrosion between the aluminum layer and the silicon layer, and the oxygen reduction on the silicon layer promote the local pH increase. Then the copper ions in the solution can form precipitate like copper hydroxide oxide. Then the hydroxide can support a higher oxygen reduction reaction and further increase the local pH and trigger the zirconium formation. Now, just summarize the H loss and also the pretreatment on the cast aluminum. So we do see a high H loss in the cast aluminum, limited by, and we see selective solution of aluminum, and then form a porous silicon-rich mouth structure. This mouth structure has a very high surface area, and it can allow more zirconium formation. So you can see a higher coating weight. So with this high etching, the decreasing high coating weight, you may see higher chemical usage or higher cost. Then another thing here, we look at the edge loss pretreatment. Also, there's some lubricant or coolant on the surface. So how they can be removed in the alkaline cleaning solution. So first we did some analysis on what's formed on the casting surface. So the blue line here is the FTR spectrum with the raw lubricant. You can see the hydrocarbon or this kind of functional group. And we also collect spectrum on the black stain area on the lab-made sample. And you see also similar hydrocarbon peak, but there are 3 bumps here or here that's not observed on the raw lubricant or the blue line here. So to have to confirm what these small bumps, we burn some lubricant in the lab just to simulate the casting process, and then we collect the spectrum on the lubricant sludge, and you do see a similar 3 bumps over here. So on the surface, you may have some partially oxidized lubricant, more like the original lubricant, but you also have some oxidized lubricant, like the sludge on the surface. Then how they can be removed in the alkaline cleaning process. So this is the wettability results on the cast aluminum. with a nominal lubricant application, you can see the surface is fully wettable. There's no water-free area, but with excessive lubricant, you potentially can have a lot of water-free area. This can potentially affect the subsequent pre-treatment, also the e-coat performance. So to better understand what really happened on this excessive, this water-free area, we look at their surface morphology change at different stage. So at the cast condition, you can see a lot of black staining. It's mainly rich carbon. And then after cleaning, you see some lubricant is removed. And also, actually, you see a lot of etching under this staining, meaning some etching really goes under the lubricant residue and then still etch the metal substrate. And after zirconium pre-treatment, not much obvious change. This is EDS further showing the presence of the lubricant residues can be very high in some local area. But some interesting that zirconium still can deposit on this carbon, maybe because the carbon is also a strong cathode. So what the staining might affect the performance? Why we care about this heavy staining? So this is the e-coat sample. So this is the cross-section with e-coat panels, and here is the e-coat. This is the metal substrate, and this is the staining, and this is the porous structure we showed before because of etching. You can see the lubricant staining can stay between the e-coat and the metal substrate or the conversion coating. In theory, the e-coat should bond with the conversion coating, not with the lubricant residue. So in certain conditions, it can affect the adhesion. If the staining is very thick or very heavy, it may leave some pinholes on the surface. So that means it's not provided by, and no e-coat formation on this area, so potentially some low corrosion performance. We also look at the e-coat performance. So with the nominal lubricant, the wet adhesion is actually very good, and also the scrap creep performance all very good. So they all meet the current specification. With this, I conclude my presentation. So first, the cast aluminum shows a bit of high etch loss in the alkaline cleaning and can have some high conversion coating weight, but the performance is robust, especially with the nominal lubricant. If you put too much lubricant, it can potentially lead some staining on the surface, make it difficult to clean in the solution, can affect some adhesion and also cause some defects in the e-coat. And the high etch loss in the alkaline cleaning may lead some porous silicon-rich layer on the surface. So last one, I want to thank all my colleagues who support this work, and without their support, it can be difficult to finish all this work. That's all my presentation. Thank you. Yeah.
Okay, so we're ready for Q&A. If you want to have someone read your question for you, you can submit it on the app in the Q&A part, not the chat. And if you are willing to speak, you can just raise your hand and I'll bring you a microphone. So any questions?
Very nice talk, Jichao. So I have a couple of questions. So the first question is about the black stain. So after the casting, so it's already become like a dry stain. So is there any method we can remove during the degreasing or the pre-treatment?
Yeah, you have other methods like the plasma laser, or you just use the sand. You can remove that, but the thing is, we see whether we can directly clean this staining in the alkaline cleaning process. So you don't need an actual process to remove the staining. So that's why we're trying to control how much lubricant you apply on the die surface to minimize the potential staining on the surface. So yeah, there are some other methods, but we need some actual process. But instead to do that, we're trying to minimize the lubricant applied on the die.
Yeah, so which means in production, so we want to have robust degreasing. What your suggestion means, probably it's still hard to remove the dry stain during the degreasing, and then the best way is still control the lube before they bake.
Well, yeah, you can, so there's a different way. So you can change the degreasing, but you also need to consider what is other impact on the metal substrate that without staining, and also other mixed material on the body structure, because you all process together. If you may have a measure to increase the lubricant removal, but you also need potentially affect other edge loss or the bare metal without the staining, or the other like the steel or thin coated steel or aluminum structure. So it's not just one simple change to remove the lubricant. You also need to consider the impact on the other materials and also other edge loss, these kind of properties. So.
Nice. So another question is about the copper, the deposition or redeposition on the silicon. So what's the copper content in this cast aluminum alloy?
So this cast aluminum alloy has low copper, it's low copper cast aluminum, and the copper is mainly from, in some pretreatment solution, they may have some additives, so they can potentially deposit on the surface. So.
I see. So the copper is actually from the pretreatment solution and the redeposition to the surface.
Yeah.
Thank you.
Do we have another question? Okay.
I can ask one from the app while we're getting the microphone. It says, what is the thickness of the zirconium oxide in this study, and what is the actual thickness of the pretreatment in manufacturing?
The zirconium thickness. So normally we don't look at the zirconium thickness. This is more like some fundamental study to see how the zirconium deposited on different phases. Normally we look at the coating weight, like we use the SRF to measure the zirconium coating weight. There is some specification, like the coating weight needs to be in the targeted range. Too low or too high is not good for either corrosion protection or adhesion. So we normally don't look at the zirconium thickness, more look at the coating weight. So there are some specification defined or validated through some corrosion or adhesion performance. So.
Okay.
Have you looked at the corrosion resistance as a function of how much etch occurs in the alkaline degreaser on the casting?
Yes, we do look at that. And actually this material is low copper, had very good corrosion resistance. And also here you may see after even have high etching, the main enrichment on the surface is the silicon. Silicon is a pretty noble element, doesn't strongly affect the corrosion performance. But it may, because this silicon-rich layer is porous, so you can imagine if you have a porous structure between the metal substrate and the E-coat, it can make affect the adhesion. But generally, this material has very good corrosion performance. But even if you change the alloy composition, you put more copper, iron, or zinc, it can be a different story. So.
Thank you.